And I will start admitting people as we go. So, hi, welcome to PWA Summit Block 2 workshops. This workshop is all about web workers, all the different kinds of web workers that exist. We are going to be focusing, or we're going to be talking about all three of them today. The workshop is, we have a 4-hour time block for the workshop. I don't think we're going to spend all 4 hours on it. There's going to be lots of time for Q&A, and there's going to be time for Q&A. There's going to be time for you to actually do some code on your own. And yeah, that'll be fun. I'm going to ask you stuff. It'll be interactive. And we've got a pretty small group. So if you've got questions, feel free to use a little raise hand icon to raise your hand, and I will take questions as we go. Prerequisites for this workshop. You're going to need Node.js on your computer, as well as a local web develop, or as well as a text editor on your computer, and the ability to download code from GitHub if you want to participate in the coding exercises. If you don't want to participate in the coding exercises, that's totally fine. You're going to have some downtime today, but it's totally fine if you don't want to do that. But that's what you'll need to participate today. Before I get rolling, does anyone have any questions about what I just said, what I set up? Or before we get started, any questions about the workshop format? Okay, I don't see any. Cool. And just in case you are interested, I don't have a slide on this, but my name is Sam. I'm a developer advocate at Google, working on Chrome OS and helping to do PWA and web stuff as well. So yeah, let's get started. And we're going to get started with a question. What kind of work might you want to move off of your main thread? Feel free to throw answers in chat, come off mute, throw scream answers out at me. What kind of work might you want to move off the main thread? Visual processing. Audio processing. Video processing. Backend service calls. Delayed jobs like sending notifications. State management. Yeah. Anything else? Okay, cool. Yeah, all good ideas. So let's dive in. So what are workers? We'll get back to the answer to that question later. So what are workers? Well, web workers let you run JavaScript in background threads, separate from the main thread and from each other, without blocking or slowing down other threads. Web workers are often underutilized, but they're widely available web capability, and they let you move work off of your main thread. Web workers run in PWAs run some JavaScript outside of the main thread. There are 3 kinds of workers. Here, let's picture 2 tabs open for the same PWA. Can I zoom in here? I can zoom in here. Excellent. So the first type of worker is what's known as a dedicated worker, and it's what's commonly thought of when you think about web workers. They can be used by a single script in a single running instance of a PWA. They can also be run from each other, but they're a one-to-one relationship. Then you have shared workers. Shared workers are similar to dedicated workers, except that they can be shared by multiple scripts across multiple open windows. This provides the benefits of a dedicated worker, but with a shared state and internal context between windows and scripts. A shared worker could, for instance, manage access and transactions for a PWA's IndexedDB and broadcast transaction results across all calling scripts and let them react to changes. And then the third type of worker is something you're probably familiar with PWAs, and that's a service worker. Service workers are actually a type of web worker. And they act as a kind of a proxy for network requests and are shared between all instances of a PWA. There's a lot you can do with workers. You can use messaging, including things like broadcast channel, to communicate between workers. They can manage your cache, fetch data, update IndexedDB, read files, and except for service workers for now, generate additional workers. But workers are also pretty limited. They can't access the DOM, including having DOM nodes passed into them. They don't have access to all web APIs either, especially ones that require user input to activate. And you can only use ES modules if you're writing a dedicated or shared worker, and then only in a Chromium browser. Again, for now anyway. The three kinds of workers letting you run non-DOM code off the main thread. What should you use them for? Well, to decide, we need to talk about complexity first. So, in his talk, Simple Made Easy, Rich Hickey discusses the qualities of simple versus complex things. He describes simple things as focusing on one role, one task, one concept, or one dimension, but emphasizes that simplicity isn't about having one instance or performing one operation. Whether or not something is simple is about how interconnected it is. Complexity comes from binding, weaving, or to use his term, complecting things together. It can be measured by counting the number of roles, tasks, concepts, or dimensions something manages. Simplicity is important in software development because simple code is easier to reason about and easier to maintain. For the web, simplicity is important too, because it may just be easier for our users' devices to handle. All JavaScript we write for the web, at least at one point, touches the main thread. The main thread, though, comes with a lot of complexity out of the box that you as a developer have no control over. The main thread is responsible for drawing the page, which itself is a complex multi-step process involving calculating styles, updating and compositing layers, and painting to the screen. It's responsible for listening to and reacting to events, including events like scrolling. It's responsible for loading and unloading the page and managing media security and identity. And that's all before any code you write that can only be done on the main thread, like manipulating the DOM, or accessing sensitive APIs like device capabilities and media or security or identity stuff. As Surma put it in the 2019 Chrome Dev Summit talk, the main thread is overworked and underpaid. And yet, most application code lives on the main thread too. All that code adds to the complexity of the main thread, which then requires more and more processing power to complete quickly, because every second it takes to perform application logic on the main thread is a second it can't respond to user input or redraw the page. The Rail performance model is a research-based, user-centric structure to help us think about performance. There are four key experiences: response, animation, idle, and load, with goals for each. The goals are based on kind of hard limits of how human perception works because, well, we're all human. These don't change based on device or the network that we're on. When interactions don't connect to input, when frames drop, or when it takes too long for a site to load, users get frustrated. They feel the application is broken, and their confidence in it decreases. The bad news, adding complexity to the main thread is an almost surefire way to make meeting these goals difficult. The good news, because what the main thread needs to do is clear, it can be used as a guide to help us reduce what's on it for the rest of our application. There are lots of different kinds of work that web applications do, but broadly speaking, it can be broken down into work that directly touches the UI and work that doesn't. UI work is work that directly touches the AI, the DOM, APIs that touch device capabilities like notifications or file system access, touches identity, like user cookies, locale, or session storage, manages media, like images, audio, or video, and has security implications that would require user intervention to approve, like the web serial API. Non-UI work are things like pure calculations, data access like fetch and index DB, cryptography, messaging, and blob or stream creation or manipulation. Non-UI work is often bookended by UI work. A user clicks a button that triggers a network request for an API, which returns results, which are parsed and the results are updated on the DOM. When writing code, this end-to-end experience is often what's considered, but what each part of the flow lives usually isn't. The boundaries between UI work and non-UI work are as important to consider as the end-to-end experience, as it's the first place the main thread complexity can be reduced. One of the most straightforward ways of simplifying code is breaking out functions so that each focus on a single task. This can be determined by the boundaries identified walking through the end-to-end experience. So first, we respond to user input, and that's UI work. Then we make an API request. API request isn't UI work. Parse the API results, also not UI work. Determine the changes to the DOM. Now, this might be UI work, or if you do something like virtual DOM implementation, it might not be UI work. And then finally, make changes to the DOM. This is always UI work. The first clear boundaries are between UI and non-UI work. Then there are judgment calls that need to be made. Is making and parsing an API request one task or two? If DOM changes are non-UI work, is that boundary within the API work? Is it the same thread? Is it a different thread? The proper level of separation here is key to both simplifying your code base and being able to successfully move pieces of it off the main thread. To be able to break up large end-to-end workflows into smaller parts, you need to think about your code base's composability. Taking cues from functional programming, consider categorizing the types of work your application does, and building common input and output interfaces for them. For instance, all API retrieval tasks take an point and return an array of standard objects, and all data processing functions take in and return an array of standard objects. JavaScript has the structured clone algorithm, meant for copying complex JavaScript objects. Web workers use it when sending data with messages, and IndexedDB uses it for storing objects. Choosing interfaces that can be used with the structured cloning algorithm will make it even more flexible in where you can run things. By categorizing your code and creating common input and output interfaces to these categories, you can create a library of composable functionality. Composable code is a hallmark of simple code bases, loosely coupled, interchangeable pieces that sit next to each other and build on top of each other, as opposed to complex code that is deeply interconnected and therefore cannot be easily separated. And on the web, composable code can mean the difference between overworking the main thread or not. With composable code in hand, it's time to get some of it off the main thread. So what does all of this look like in practice? Well, let's talk about state management. State is one of the biggest sources of complexity an app can have, itself being a complex expression of values over time that pushes complexity onto everything it touches. It is also all non-UI work and essential to a lot of modern application development, so it provides an excellent example of how to consider simplicity and complexity, especially with the main thread. State-driven application development is a really powerful tool for managing complex user interfaces. It's commonly made up of three parts: the view or UI layer, an actions layer, and a state layer. The view layer listens for events that would trigger a change in state, a change in authentication, a UI event being triggered, or the like, and calls an action, often with a payload describing the change. For instance, it could call the update user action with a payload of a user object. Anywhere the view layer needs to know about the state change, it can subscribe to state updates from the state manager. The action then routes the payload to the correct update to correctly update the state. And finally, any state subscriptions are informed of the new state, allowing them to act accordingly, like updating the DOM. Applying the separations of concerns breakdown that we just talked about, the view layer of state-driven application clearly falls within UI work. The actions and state layers, though, do not. These two layers are often considered together and referred to as a state manager. State management, by its very nature, is asynchronous, usually only contains items that can go through structured cloning algorithm, and has clearly defined and shared input and output interfaces, all of which make it an ideal candidate for moving off the main thread. This pattern works for both dedicated and shared workers. Here, though, we're going to show it with a shared worker to allow for shared state across PWA instances. With the general shape of state management in place in the worker, the view layer of the main thread can send a message with the action it wants to make to the worker. The worker can then act on the state, update it, and when complete, send out a message to all connected instances where the view layer subscriptions can fire and act on the updated state. So let's take a look at what this might look like. This example builds a shared worker state manager by using a state class with two private properties, the internal state as an object and subscribers as an array. It exposes an asynchronous method action that takes in an object with type and payload properties, and a subscribe method that takes in a callback property for the function to call when the state change occurs. The action method determines what state change should be, and once made, calls the subscribers. There's one problem with this code from a worker's perspective. The subscribe method takes in functions, but functions can't be passed to workers. Coordinating this with just post message, which is how you communicate between workers, can be a daunting task. You need to set up a function identifiers for each function, created, pass those identifiers to the worker, have that worker send a message with the right identifier, and then call the right function on the client with that data for the right identifier. And you need to do all that with just the post message interface. It's a lot. Instead of doing that, though, we can use comlink. It's a small library, a couple of kilobytes minified, to make working with workers feel like working with any other bit of asynchronous code. For the state manager, this means being able to use the class as if you had directly instantiated an instance of your client, including using functions without manually managing messages. So to finish setting up this worker, after importing expose from comlink, we create a singleton instance of our state and expose that to each connecting instance of our worker. Then from the client, two more comlink features are used. First, after creating a shared worker using the standard shared worker function or instance, it gets wrapped by comlink. Doing so enables almost seamless usage of what's exposed from the worker, with the exception that everything is now asynchronous. So here, we're creating a shared worker. We're pointing to our worker. We're saying type module. For now, we're going to use modules. And we're wrapping the shared worker. So if you're doing a dedicated worker, you don't need to wrap the port. If you're doing a shared workers communicate over ports. So you need to wrap the port. From there, the state manager's subscribe method can be called. Because functions can't be passed between worker boundaries, comlink's proxy function is used and acts as an intermediary between the two. Finally, we use our action method as if we had a regular class. So await state.action. So it's code time. Here is where you're going to get a chance to actually try this out. So if you follow this link, you'll be greeted with a code lab. Code labs are self-paced sets of code that will walk you through a set of instructions to get some code working. You're going to be working on a sample app called PWA Edit, which is a in-browser markdown editor. If you go to this link, it'll give you the code lab, I will actually go to this link myself so you can see what it looks like. I will share it in chat. Give me 1 second. I need to find where chat went on my end. There's chat. That is the URL. Share this tab. So you will be taken here. In the Get Setup section, you can clone the repo or you can download the zip. If you're going to clone the repo, make sure you start with the PWA 06 working with workers branch. Make sure you check out that branch because that is what will have all of the previous work in this series of code labs done for you already for you to start with. You also need node 14 or higher. Make sure you run npm CI to install the dependencies, and then you can run npm start to start development. Otherwise, you have 30 minutes to walk through this code lab to set up a shared worker using a state manager using a shared worker. Does anyone have any questions before we get started? OK, if you have questions during the code lab, feel free to raise your hand, throw something in chat, scream something out, and I'll answer them. I will meet you back here at top of the hour. Okay, everyone, that's 30 minutes. If you weren't able to get through everything, that's totally fine. The code lab is going to stay up, and you can get back to it when you have more time. So we've talked about shared workers. We've talked about dedicated workers. Now let's talk about service workers. So we're going to spend the rest of today talking, kind of going in depth in service workers. So our users expect apps to start up on slower flaky network connections, or even when offline. They expect the most recent content they've interacted with, like media tracks or tickets and itineraries, to be available even if getting a request from your server is hard. When a request isn't possible, they expect to be told there's trouble instead of silently failing or crashing. And they expect to do it all quickly, with a recent study, Milliseconds Make Millions, showing that even a 0.1 second improvement in load times can improve conversion by up to 10%. A reliable progressive web app is one that can depend on and responds to the needs of users in the blink of an eye. Taking your PWA offline is a great way to make it reliable for varying network connections and to speed up performance even when network connections are great. So I have a question for all of you. What could an in-browser proxy help make? How could an in-browser proxy help make your PWA work offline? Feel free to answer in chat, raise your hand, come off mute. Resource loading, caching local files, anyone else? An in-browser proxy is a proxy that works in your browser. If you don't know what it means, that's okay. That's what we're going to go over right now. Anyone else? Okay, let's keep rolling. The two main features that let your PWA work offline are service workers and the cache storage API. Service workers are an in-browser proxy or an intermediary for requests between your PWA and the server or servers that power it. The cache storage API allows you to directly manage items in your browser's site cache. Together, the two can be used to manage where a PWA gets its resources from. So let's look at what the lifecycle of a proxied request is. In order to start proxying requests through a service worker, it first needs to be installed. The first time your user comes to your PWA, the request will go directly to your server. After checking to see if the browser supports service workers, your PWA can register a service worker to act as a proxy. When loaded, the service worker then sets up shop between your PWA and the server, allowing it to intercept requests for resources and, amongst other things, control your browser's cache through the cache storage API. When a request that's covered by a service worker is made by the browser, including when you're offline, the service worker will intercept the request, acting like a proxy server. It can then decide if it should request the resource from cache via the cache storage API or from the network. It then returns the resource to the browser. Service workers have their own lifecycle that dictates how they get installed, what they can proxy, when they're able to proxy requests, and when to update with a new version. The service worker lifecycle starts with registering, so let's look at service worker lifecycle starts with registering a service worker. The scope of a service worker is determined by the folder it sits in, literally the folder on your server. So a service worker that lives at example.com/app/swjs can control any file at the app path or below, so app/foo app/bar. Service workers can only control items, pages, workers, collectively clients, in that scope. Because of this, you should put your service worker as close to the root of your app as possible, not put it in, for instance, a JavaScript folder or have it loaded from a CDN. So let's take a look at some examples. If you have your service worker located at example.com/app/sw.js, is example.com/app in scope? This is a question. These are all questions for the group. So feel free to answer in chat or come off mute and answer. Is example.com/app in scope for this service worker? Yes. Anyone else? Yes. Yes, it is in scope because it matches root of scope. What about example.com/app/css/style.css? Is that in scope for the service worker? Yes, also in scope. Yes. Yep. Yes, it's beneath the root of scope. What about example.com/other app? Is that in scope? The answer is no. Other app is above the scope of the app folder. Remember, the service worker lives inside of the app folder. This is outside of the app folder, so it's no longer in scope. What about example.com/js/shared.js? Is this in scope? Nope, 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 nope. Nope is correct. It's again out of the app scope. Once a service worker is registered and it's downloaded and parsed successfully, it gets installed. The service worker's install event will fire. Install events only fire here. If you want to change what happens during install, you need to update your service worker. After the service worker is installed, it's ready to control clients. It sends an active event, but that doesn't mean the page that registered the service worker will be controlled. By default, you'll need to refresh the page for that to happen. So when your service worker first gets installed, it's not controlling anything. It just runs through the install event and then activates. But it's not controlling the page you're on. So things won't go through your service worker yet. It'll only control the page after it's been installed and activated and you navigate to it once more. So you will always have at least one request, one page load that does not go through your service worker for every user. Service workers get updated when the browser detects that the actual service worker file is byte different than the one currently controlling the client. Because of this, when updating a service worker, you should update the existing file without renaming it, including adding file hashes to the file name. Otherwise, the browser will never get the new version of your service worker. So, for each of the following, tell me if the service worker will or will not be updated and the reason why. So, example.com/app/sw. There is our base service worker, and the new service worker is example.com/app/sw.js, and no content has changed. Will this be updated? Will this trigger a service worker update? No. No. No, because no content change. Correct. No content change in the same service. It has the same service worker path. What about example.com/app/sw.js and the content has changed? The answer is yes, the content has changed and the service worker is at the same path. So if we add a hash to the path, then the URL is now different. And because the URL is different, the service worker won't see the new content and it won't ever get updated. So you always need to have it the same path without any hashes. If you have a hash in your service worker URL, then it will not be considered the same file path and it will never be found. So you can't actually update your service worker. This is that question. This is a hash, example.com/app/sw.12345.js, and the content has changed. Will this trigger an update for your service worker? Correct. No, because this is now a different service worker path. Even though it looks to us like this might just be a hash, it is a different path. And because it's a different path, it will never be found trying to update it. Does this mean that new files in a project are simply not recognized by service worker? No, that's not what it means. You can have as many new files as you want. The only limitation is that the actual physical path to your physical service worker file must always stay the same. Other files across your app can change as much as they like. You can have hashing, you can do whatever you want. But the physical path to your physical service worker file, and only that service worker file, must always be the same once it's been registered. Cool? Cool. Let's look at this one. What about example.com/js/service worker and the content hasn't changed? Will this trigger service worker update? No, no, no. Nope. Correct. It's a different service worker path. Will not trigger an update. What about that with the content having been changed? No, no, still a different path, still a different path. You're all correct. Still a different path. So how do we manage changes to our service worker if we can't hash the file and we can't change the file name? Well, instead of versioning the file name, instead consider a best practice of changing the name of your cache inside of your service worker file, or changing a comment or a const number inside of your service worker file. Instead, this will prevent, by changing the cache name, it'll prevent the old cache from being overwritten, which still might be used by your old service worker file. So let's look at what updating looks like. After being successfully installed, a new service worker will wait to the active event until the existing service worker is no longer controlling any clients. This is called the waiting period, or waiting. And it's how browsers ensure that only one version of your service worker is running at a time. Simply refreshing a page won't actually move you out of the waiting state, and it won't let your new service worker take effect. You need to physically close or navigate away from all tabs using the current service worker and navigate back to it before the new service worker will take effect. There's also something that we'll talk about a little bit later on where you can signal to your service worker to skip the waiting and let you just reload. But in general, waiting, your service worker won't actually activate after being updated until you closed all tabs and reloaded, or navigated away and reloaded. So let's talk about how do we debug service workers and the cache storage API. It can be tough sometimes. Chrome DevTools, though, has a number of built-in tools to help make this easier. So if you open up Chrome DevTools, you'll see an application panel. Clicking that panel gives you insight into a number of items that are otherwise hard to inspect about running website. Here, our focus is going to be on the service worker tab inside of that panel. The Service Worker tab gives you a slew of information about the currently installed service worker. It'll show you what clients are currently claimed by the service worker, the source of the service worker, its status, and let you test things like push and sync. Here, if you have the service worker in a waiting state, you can skip the service worker's waiting lifecycle by clicking Skip Waiting. Doing so will immediately promote the waiting service worker to active. You'll still need to reload the page to have it take control, like the normal service worker lifecycle. In the same pane, you can also check and enable the bypass for network checkbox. Doing this will treat your site as if it doesn't have a service worker installed at all, directing all requests through the network. Be cautious when enabling this checkbox, though, as the setting persists across tabs and even sites. So once it's enabled for all browsing until you turn it off. Also in the service worker pane is an offline checkbox. Checking this will simulate the current tab being offline. This will let you browse your PWA as if there's no internet connection. This setting persists until Chrome DevTools is closed. There's one more checkbox in this area, Update on Reload. When the checkbox is checked, every navigation will refetch the service worker, install it as a new version, even if it's byte identical, skip the waiting phase so the new service worker activates, and navigates to the page. In short, you'll get the full service worker lifecycle for each navigation, including the refresh, without having to reload twice or close the tab. While there are some uses for the setting, you should consider using it only as your last resort for debugging your service worker, as it creates a different lifecycle than what your users will use, and, like bypass for network, is sticky between tabs and sites. Instead, you should consider using an incognito mode tab to test fresh installs of your service worker, or the normal lifecycle with skip waiting instead. So it's code time. We have, I can't copy that, fabulous. I will just type the link out. workshops.page.link/PWA03. So, of course, that didn't actually work as a URL. You have another 20-minute code lab. This code lab is going to guide you through writing a service worker from scratch. Same as last time. I will give me 1 second to pull it up for you all. Same as last time. If you already have the repo cloned, you can instead check out the starter branch and get started from there. If you downloaded a zip, you can download the zip again. And you can start working on this. And this will have you write a service worker from scratch. Does anyone have any questions before we get going? OK. You have 20 minutes for this. When doing this, you might have a service worker installed from the previous exercise. Go to the applications panel and unregister it. There's a button that will say unregister, and then you can get started with your code for this workshop or this code lab. If there are no questions, you've got 20 minutes. Go ahead and get started. Okay, everyone, that's time. So you've just done some simple service worker and cache storage API stuff, simple use cases like the work done in your code lab. Those simple use cases can be pretty straightforward to write and maintain, but there are many different caching strategies you could employ depending upon the needs of your PWA. So I have a question for y'all. Again, feel free to answer in chat, come off mute, and respond. How might you cache frequently updated content? What about infrequently updated content? Might you cache those things differently? What do y'all think? Anyone? So what might be different about them? No? Frequently updated content needs updating always. Okay. Or nearly always. Okay, let's take a look. So imagine this. You're running a newspaper website and have the last month's article available. The articles may get updated, but after the first week's worth of reporting, probably don't. If a user accesses these articles, it's probably okay for them to get a cached copy instead of getting a fresh copy. When having the most up-to-date resource is not vital for our user, a good caching strategy is one called stale while revalidate. The stale while revalidate strategy has requests attempt to respond with a cached resource if one is available. If one isn't available, it falls back to a network request if it hasn't been cached. A network request is used to update the cached resource after the cached resource has been served. So it tries to serve a stale one from your cache. If a stale one exists, it responds with that. If it doesn't, it'll go to the network or try to go to the network, serve that, and cache the result from the network. Instead, let's think about archive news. Now you're working, instead of archive news, let's think about working on like a business homepage, which includes all of the breaking news of the day, as well as like real-time stock prices. Your users need to see the most up-to-date content as it's available, only accepting a cached version if they've got no other choice. For this, a network-first caching strategy might be a good idea. By default, the network-first strategy will try to fetch the latest version of a resource from the network. If the request is successful, it'll serve that to the user and store it in the cache. If not, it will respond with a cached version. So this will always try to serve whatever the latest thing is from your network. The opposite of network first is cache first. Images are often cached this way because while the image used in an article might change, the actual source for the given image isn't likely to once it's been downloaded. So you might change from like a picture of a cat to a dog, but the dog picture probably isn't going to change. With this strategy, resources are checked to see if they're in cache before trying to go to the network. If they are, they're served. If not, they're retrieved from the network and a version is stored in the cache. This strategy usually doesn't have a built-in mechanism for updating cached items, so be sure to use it in conjunction with another way to update what's cached, like expiry headers or resource hashing. And then the cache-only strategy is similar to the cache-first strategy, except that the resources can only be retrieved from the cache. You'll need to get the items into the cache without relying on a network fallback if the resource isn't there. It's good for resources that should be updated when your service worker updates, like an offline fallback page, as that's the most common time these resources will be updated. And finally, there's the network-only strategy, which can be thought of similarly to how browsers behave without the use of a service worker or the cache storage API. Requests will only be able to respond with a resource if it can be fetched from the network. This is often useful for resources like online-only API requests. There are two questions you should ask yourself when trying to figure out the caching strategy to use for any given asset. How frequently is it updated, and does it depend on something else? The answers to these questions can help narrow down how to manage your cache. For instance, an item that's frequently updated and doesn't depend on something else, for instance, homepage content on a new site, should probably be cached with a network-first strategy. Items that are infrequently updated and have no dependencies, like an interior article, should probably be cached with a stale while revalidate strategy. Items that are almost never updated and have no dependencies, like an image in an article, should probably be cached with a cache-first strategy. On the other hand, if assets that are infrequently updated but have dependencies on each other, for instance, shared JavaScript and CSS, you might want to cache with a stale or validate strategy, but also cache the latest version when the service worker installs to ensure that they start using your same version on updates together. You may also have assets that are dependent on the service worker, like an offline fallback page. For these, you may want to cache with a cache-only strategy and cache the latest version when the service worker installs, a pattern commonly known as pre-caching. Managing service workers by hand can be a cumbersome task filled with lots of gotchas when you move past the most basic service workers. Workbox is a set of libraries distributed as NPM modules to help you write scalable, maintainable service workers. Managing what caching strategies to use for what matching routes is a core strength of Workbox, allowing robust rules to be written to manage your PWA's reliability. The Workbox module, Workbox Strategies, comes pre-built with the caching strategies we just discussed. The Workbox routing module helps to manage matching incoming requests to your service worker to caching strategies or functions to manage those requests. These two can be combined to manage how your service worker responds to requests, with the cache response plugin helping determine whether a response should be cached. Note, while Workbox is distributed as NPM modules, service workers themselves don't yet support ES module syntax. So the code that I'm going to show you here will need to be compiled before it's usable. So let's take a look at an example of this. So here we're going to set up a strategy for a page. It's a network-first strategy. Here, the cache name option and the plugins option are used. The cache name option determines the name of the cache requests will be stored in. The plugins option allows you to tap into a number of different aspects of the lifecycle related to caching and resolving requests. Here, the cacheable response plugin is used to only cache requests that have a 200 status, preventing bad requests from being saved into the cache. Caching strategies can be used with multiple registered routes and can even be called by themselves to handle requests without a route. So if you think you may need to do that, saving it as a variable is a good choice. With a strategy created, it's time to register a route to use the caching strategy. There are two primary inputs to the register route function that Workbox provides: the matcher and the handler. The matcher is either a callback function that gets passed an extendable event, a request, or a URL object, or it's a regular expression to match against the request URL. In either case, it must return a truthy value and it must be synchronous. The handler is a callback function that gets passed the same arguments as a matcher, plus a params value, which is the value returned by the matcher. The handler must be a promise that resolves to a response. Here, the matcher looks to see if the request is in navigation, and if it is, uses the network-first strategy we just defined. The Workbox routing module also has an export set catch handler that provides global handling if a route throws an error. This can be used to set up offline fallback to notify users that their requested route isn't currently available. Here, a combination of Workbox and the cache storage API are used to provide an offline fallback using a cache-only strategy. First, during the server worker's install lifecycle, the offline fallback cache is opened, and once opened, the array of offline fallbacks is added to the cache. Then, in set cache handler, the destination of the request that threw is determined, and the offline fallbacks cache is opened. If the destination is a document, the content of the offline fallback is returned to the user. If that doesn't exist, or the destination isn't a document, a normal error response is returned. This pattern can be extended not just for documents, but for images, video, fonts, really anything that might not be in cache, but you want to provide a fallback for when offline. There are a number of routing caching patterns, like network-first navigations and offline fallback, that are common enough to be standardized into reusable recipes. Where one of these common patterns matches your needs, the Workbox recipes module makes them easy to consume and implement. This example shows both of the previous examples implemented using Workbox recipes, plus a recipe that caches Google font requests with stale while revalidate strategy, and a cache-first strategy for the underlying fonts. So, more code time. If you go to Workbox, I can copy this one now, can't I? Yes, I can. If you go here, you will have another code lab. Let's take 20 minutes to do. Same deal as last time. If you have already done, or same deal as last time, you can get started by changing to the PWA 03 Workbox branch and working through this code lab to use Workbox as part of your service worker. I'm going to give you 20 minutes to do this. Does anyone have any questions before we get rolling? Okay, I don't see any. I'll see you back here in 20 minutes. Again, if you've got questions, feel free to unmute yourself or throw them up in chat. Is Workbox an offline dev tool rather than something that works on the server? Yes, Workbox is a library that works in your service worker as opposed to something that works on the server. So when you're using Workbox in your service worker, you're going to be shipping Workbox code as part of your service worker to your users. Let me take a look. So yeah, that appears to be a pretty basic service worker. There doesn't seem to be something um, immediately jumping out at me. Um, it's not a complex service worker, so I'm not quite sure exactly what you're going for here. It just looks like it caches everything with a stale or revalidate strategy. Um, you might not actually want a stale while revalidate strategy for everything, but that does appear to be using Workbox, and it does appear to be using a stale while revalidate strategy for everything. So in the service worker you just linked, it is downloading all of Workbox directly from a CDN. That's not the recommended way to use Workbox. It is recommended that you only pull in the individual files you need, like we're going to work through in this code lab, which also means you need some kind of JavaScript bundler to bring it all together. So it's hard for me to tell you what files do you need to ship. It's going to be really based on what you want out of your service worker and what functionality from Workbox you're using. Workbox isn't a single file. It's a lot of files across a lot of different tools, so you can pull in only exactly what you need. Okay, everyone, we're back. Share this tab instead. How was that for everyone? So now you have built service workers without any third-party code. You've now built service workers with Workbox. The last thing is to look at some advanced service worker patterns. So an emerging pattern for leveraging service workers as an integral part of site architecture, as opposed to just site caching, is something that I like to call service worker includes, which divides individual assets up based on their caching needs and stitches them together in the service worker in order to improve consistency, performance, and reliability, all while reducing cache size. So if we're looking at this page, how might we cache this page? What are the different ways we could cache this page? Again, feel free to throw stuff in chat or come off mute and answer or say something. Caches referenced asset, images, JavaScript, etc. What else? Okay, let's take a look. So for me, it's not just images, JavaScript, CSS. There are actually 5 different sections of this page that we can break down. The first is the overall layout of the page. The second is this global header. The third is this content area, the middle left lines. The next is the sidebar. And the last is this footer. The overall layout isn't likely to change often and doesn't have any dependencies. So this might actually be a good case for something that we can pre-cache, something that we can load into our cache at service worker install time. The global header and global footer might contain things like the top menu and the site footer and present a somewhat unique challenge. If the page were to be cached as a whole, those might change between page loads depending upon when the given page was cached. By separating them out and caching them independently of the content, you can ensure that the users will always have the same version of those items regardless of when the content was actually cached. Because they're infrequently updated, they're also a good candidate for pre-caching. They have a dependency though, and that's the site's CSS and JavaScript. The site's CSS and JavaScript I usually think of as good candidates for the stale while revalidate strategy to allow incremental updates without needing to update the whole service worker. But they also need to be kept at a minimum version whenever the service worker updates with a new global header or footer. Because of this, their cache should be warmed when the latest version of the service worker installs. Next is the content area. Depending on the frequency it gets updated, it could either be network first or stale while revalidate. The image should be cached with a cache first strategy, as has been previously discussed. And then finally, presuming that the sidebar content contains things like page tags and related content, it's probably not critical enough that we pull it from the network every time. A stale while revalidate strategy could work for this. Now, after going through all of that, you might be thinking that this kind of per section caching can only be done for single page apps. But with some advanced service worker features, this can be done for any architecture, single page apps, even multi-page apps. In the single page app world, the previous page would be created using the app shell model, where the app Chrome is cached, then served and content is loaded in client side, With the introduction and wide availability of the Streams API, both app shell and content can be combined in the service worker and streamed to the browser, giving you the caching flexibility of app shell with the speed of a multi-page app. It does this because streams can be built asynchronously, allowing different pieces of the stream to come together from different sources. The requester of the stream can start working on the response as soon as the first chunk of data is available, instead of waiting for the entire item to be complete. And parsers optimized for streaming, including things like the browser, can progressively display the content of the stream before it's complete, speeding up perceived performance of the response. Thanks to these three properties of streams, architectures that are built around streaming usually have a faster perceived performance than those that aren't. Working with the Streams API, though, can be challenging as it's complex and very low end. Fortunately, Workbox to the rescue again. You can use Workbox to help set up streaming responses for your service worker. The Streams strategy is slightly different than other strategies that Workbox offers. Instead of creating a new instance, it's a factory that creates a strategy. It also doesn't have typical things like a cache to use or plugins, because the result is created dynamically from other cached sources. Instead, it takes an array of functions that return a response, a readable stream, or a string. A string or a promise that resolve to one of those first three. The items in the array are the steps that get called to build the stream, with a portion of the stream being released to the browser after each step. In this example, the stream gets a file, head.html, from a caching strategy called static cache. The configuration of that caching strategy determines how that file is cached and retrieved. Ideally, items early in a streaming response are already in the cache, so they can be sent to the browser quickly. This can be generated server-side and can be a single tag or a useful chunk or whatever HTML you need at the end of the day. This all just gets concatenated together into one big HTML string, or one big string in general. It doesn't need to be HTML. Next, a string is added with the current date. Third, an async function is called to build the body. Functions in a streaming strategy have access to the current event, request, URL, and optional parameters of the route being requested. In them, you can do whatever you'd like to build out a response. You could fetch some content and return the HTML, combine items from the cache together to dynamically generate a page, or even call an API and use a templating language to build the response on the fly. Finally, foot.html is retrieved from the static cache just like the head. A streaming strategy like this will get important parts of your HTML, like the head with CSS and JavaScript links, and high-level static assets like the menu, sent to the browser and rendered quickly. Then, slower parts of the page, like the content in the body area, can be asynchronously generated and sent when available, all without blocking the browser from doing its work. This pattern can be extended beyond the head, body, foot app shell model. Instead of one function to build the body, you could have many, releasing new HTML into the stream as it's available. You could have lightweight templating for the head to inject meta information from IndexedDB, or you could enhance that meta information client-side. You could even perform on-the-fly image transformations and stream the results to the browser. A stream-based architecture lets you take advantage of the optimizations browsers have made to get sites rendered quickly, while maintaining flexibility in how to cache and serve your content. So we're going to try this out. This is the last code lab for the day. If you go to this URL, PWA 06, you go to that URL, share this tab instead. Same deal as we've had all day. Download the zip or clone the repo and work on this. This will have you set up a streaming markdown renderer in your service worker. to render things on the fly from your service worker. I'm going to have 20 minutes to do this. Does anyone have any questions before we get rolling? Okay, if you have questions, feel free to throw them in chat or ask me coming off mute. Enjoy. Go have fun. Okay, everyone. I hope that final workshop was interesting, showing you how you can stream content to your browser from a service worker and really generate new things. So with that, we are done with the workshop. I set aside some time for some Q&A. If you have any questions, feel free to ask them now. Again, come off mute, ask them in chat, feel free to raise your hand. But yeah, if you have questions, feel free to ask them. The recording will probably be posted on the PWA Summit YouTube channel. Yep. Any other questions? No other questions? If there are no other questions, then that's it. Thank you all very much. Have a great rest of your PWA Summit. Bye, everyone. You're welcome. Stop recording.